Okay, so hello everyone. Thanks for coming. Today the brief of my thesis is the design of compact antennas with metasurface for wideband and wireless applications. So here is the outline. First, I'll briefly discuss about the objective of the thesis. Then I'll one by one go through the topics. I'll start with the design of compact spiral antennas by modifying the metallic plane close to it, and then by modifying the absorbing mechanism with the antenna. In the next part, I'll investigate the beam tilt of spiral antenna using two different techniques, with a lens and with a metasurface. Then at the last part, I'll discuss about the design of reconfigurable metasurface based modulator structure, which is used for channel modulation. There I'll discuss about the numerical investigation as well as complete experimental validation. So as the title of the presentation suggests, we have worked on design of compact antennas using metasurface geometries for fundamentally two different applications. One for wideband application, which is for sensing and detection, especially for electronic warfare. Second one is for spatial modulation to communicate in a multipath environment. So for the first applications, we have used spiral antenna as the primary radiator. We have investigated a reference spiral antenna, then the effect of a spiral antenna above a flat metallic plane, then by modifying the geometric profile of the metallic plane, and then by using different kind of absorbers in the spiral. In the second part of in the second section of the first part, we have investigated beam tilt by loading the antenna with a bulk material properties and then replacing the bulk material using a metasurface. In the last part, or the second part, we have investigated spatial modulation technique using a reconfigurable metasurface, and the responses are investigated with a fabricated prototype. So all this work we have numerically investigated, prototypes we have prepared, we have designed the prototypes and then carried out measurements. So metasurface has been there for a few decades now, which has been used widely from acoustics to optics. For RF application, especially for antennas also, metasurfaces are widely used for antenna performance improvement, gain improvement, RCS reduction, multi-beam generation, tilting the antenna main beam, imaging, etc. Also, in recent years, metasurfaces are used to develop a complete wireless system, especially for multi-user communication and using programmable metasurfaces. Now, spiral antenna has been there for almost 70 years as a wideband radiator, and people have worked extensively on spiral, especially to make the design compact. Now, even after 70 years, we face that designing a compact spiral antenna for a wideband application, typically for 1 to 18 gigahertz, is still a very big challenge. So let's start the design of a reference spiral antenna. This is the reference spiral antenna that we have used for our investigation. It is an Archimedean spiral. We have used an 8-turn Archimedean spiral antenna from a reference, and it has an outer radius of 32 mm. So this antenna can typically work above 1.5 or 2 gigahertz frequency range. The beauty in this spiral antenna is it is simple, it is planar, and the outer and inner radius directly scales to the minimum and maximum frequency of the antenna. So we simulated the spiral antenna structure and plotted the impedance matching S11, gain and axial ratio. These are the parameters we use to characterize a typical spiral antenna. For S11, we saw S11 less than minus 10 dB from 2 to 18 gigahertz. So it has a very good impedance matching over the entire frequency range. It has a gain in between 3.5 to 6 dBIC over the entire range, but it has an axial ratio less than 3 dB after 3 gigahertz. So this antenna works as a circularly polarized and radiator after 3 gigahertz. Now what happens, we feed the power at the center of the antenna, and then that power actually gradually goes towards the perimeter of the antenna. And at each frequency, a current ring is formed. So the current ring, perimeter of the current ring is actually equal to the free space wavelength of that frequency. So higher the frequency, smaller the current rings for the entire frequency band. One thing is the antenna radiates on either sides of its axis. That means it is a bidirectional radiator. But for practical applications, we place the antenna close to a metallic plane. By placing close to a metallic plane, the radiation patterns becomes unidirectional, as you can see here. Although placing the antenna close to a metallic plane produces secondary effects. So what happens here is a schematic of the antenna above a flat metallic plane I have shown. What happens? The power fed at the center that propagates slowly towards the perimeter. Now at the low frequency, since the wavelengths are long, more power is getting coupled with this metal below. As a result, the radiation resistance at the low frequency degrades. Now, once the radiation resistance, radiation efficiency, so radiation efficiency at the low frequency degrades. Once the radiation efficiency degrades, what happens? The low frequency power remains unradiated. Those power travel at the edge, get reflected and comes back to the antenna feed and degrade the low frequency impedance matching and the axial ratio. As you can see the red dotted curve. So how can we overcome this degradation? This degradation can easily be overcome by placing an annular absorber. If you place an annular absorber close to the antenna boundary, so this can absorb this residual current or waves and can improve the low frequency S11 as well as the axial ratio. Now, what happens if we vary the distance between these two? So for different distance, we have summarized the axial ratio as well as gain of the antenna. You can see, as I've already said, that by placing the spiral close to a metallic conductor, the low frequency components are getting coupled, or trapped. That actually affects the axial ratio at 2 gigahertz and gain at 2 gigahertz, meaning closer the antenna and the metallic plane, poorer the axial ratio and lower the antenna gain. Now, what happens if we increase the antenna, the height above the conductor? By increasing the antenna height, as you can see 10 mm and 12 mm here, we can see sudden changes in the gain pattern. Okay, the gain doesn't remain flat at all, it changes. This is due to the interfering elements. That means due to the interference between the antenna field and due to the reflected field. So we have to be very careful for selecting the distance between these two. So if I just summarize things, if the antenna is close to the metal, we have a bad axial ratio and gain at low frequency, whereas the gain at high frequency is flat. If the height is more, then the low frequency axial ratio and gain are better, but there are ripples in the high frequency gain. So to combine the benefits of different antenna heights, we investigated a conical structure. What we did, we maintained a small height near the high frequency active region and a larger height at the low frequency active region. So essentially it's a conical geometry. Now we have defined a parameter here which is called delta G. Delta G, what is delta G? Delta G is used to see the difference of maximum and minimum gain between 10 to 18 gigahertz, because all the interferences we see is in between 10 to 18 gigahertz. So to quantify that variation, we have defined delta G. Now, when the antenna is placed only 5 mm above the antenna, 5 mm above the ground plane, you can see at 2 gigahertz the gain is less. At 2 gigahertz axial ratio is above 3 dB, it is bad, but the delta G is very small, means the gain is very flat after 10 gigahertz. When we are placing it above 12 mm, the gain at 2 gigahertz is better, axial ratio is less than 3 dB, but we have a very bad delta G, it is 12 dB. On the other hand, when we use the conical thing, you see the gain is slightly better, axial ratio is still less than 3, it is good, and the delta G is significantly improved about 12.7 dB. So actually, this conical structure has actually put together the benefits of antenna of these two antenna heights. Now we have extended the same structure with a modified conical structure. What we did, we proposed this modified conical geometry, which is nothing but a combination of a flat area and the conical area, and we changed the radius of this flat area. Now, by setting the radius equal to approximately 12 mm, we got a very flat response. You can see a delta G of 1.1 dB. So between 10 to 18 gigahertz, the gain response became almost flat without affecting the low frequency responses significantly. We also compared this response with a step, directly two-step antenna cavity, which was there in the available in the literature, and we saw that our system actually gives a better delta G compared to this structure. So we've performed some more numerical investigation to optimize the geometry and fabricated the optimized structure. You can see it is fabricated on an Arnold substrate, and here is the geometry of the truncated profile, truncated conical profile. I think someone is not muted. Hmm? Hello? It's okay. Okay. So we measured the antenna inside the anechoic chamber. So first, what you saw, the S11 of the antenna is less than 10 dB throughout 2 to 18 gigahertz. So antenna has good matching over throughout the band. We measured the axial ratio, and for most of the point, the axial ratio is less than 3 dB. So it has a good circular polarization. We plotted the right hand and left hand circularly polarized gains, RSCP and LSCP. We achieved a maximum gain of approximately 8.6 dBIC at 10 gigahertz, and the gain is actually restricted between 5.8 to 8.6 dBIC over 10 to 18 gigahertz. We also plotted the radiation pattern for two principal planes at different frequencies, where we can see the right-hand pattern is maintained over a wide beam. So this is the summary of this section. We investigated a reference antenna for 2 to 18 gigahertz. We investigated the effects of metallic plane close to the antenna, and subsequently we investigated a conical geometry and a truncated conical geometry, where with a very small cavity height, we are able to get good impedance matching, axial ratio, and gain. So we thought that since fabricating a truncated conical geometry, because it's a non-planar geometry, it's tricky. So we thought of replacing that one with a flat geometry, but placing the antenna extremely close to the flat metallic plane. So we place the antenna only 5 mm close to the flat metallic plane. But as I already said, it degrades the low frequency performance of the antenna. So we investigated absorbing mechanism that will be effective to remove this low frequency components. So two different mechanisms have been discussed here, one with an absorbing material, one with a set of lumped resistors. When we use an absorbing material, by reducing the inner radius of this absorbing material, the axial ratio at 2 gigahertz can be improved. But at the same time, the gain at 2 gigahertz is sacrificed. On the other hand, when we have lumped resistors, we can get a very good axial ratio at 2 gigahertz. Although between 3 to 5 gigahertz, the axial ratio is still not good. But the beauty is we do not affect the gain response at all. So we take this idea and put both of them together with appropriate dimensional matching. Means the inner radius of this material was appropriately matched with the lump resistors. And what we saw, the axial ratio, we got an axial ratio less than 3 dB throughout the entire frequency band, and without sacrificing the antenna at any point of this frequency range. Although this technique did not work below 2 gigahertz. As you can see, I have simulated the structure from 1 to 18 gigahertz. So this technique, this hybrid technique could not work below 2 gigahertz. What we did, we first increased the number of turns so that the antenna resonates at a lower frequency. Despite doing that, we could not make the axial ratio less than 3 dB at 1 gigahertz. So we realized for a better absorption technique. And with that idea, we replaced this absorbing ring, material ring, with a metasurface, as you can see here. So the metasurface is actually printed on the opposite side of the antenna substrate. It consists of metallic patches, which are arranged in a circular array in 3 concentric loops, and lumped resistors has been connected in between the patches. The entire antenna and metasurface assembly is placed just 5 mm, which is almost lambda by 60 at 1 gigahertz, 5 mm above a flat metallic cavity. So we have characterized the unit cell of the metasurface by placing it below a 3-wire differential line. So this 3-wire differential line is to replicate the spiral arms. So the 3-wire differential lines has the same dimension as the spiral arm. what we saw, by varying the length, width, and the resistor value of this unit cell, we could get approximately 30% of absorption at the low frequency, means at the between 1 to 6 gigahertz. If you look into the electric field distribution, the power is transmitted from port 1 to port 2 without any attenuation when there is no unit cell, whereas significant absorption is there in presence of the unit cell. Now this 30% absorption can be increased if we put more number of unit cell in the series. So after the optimization of the unit cell, we made the geometry, we made the entire meta surface, pasted it on the opposite side of the antenna substrate. After that, we performed some more parametric variation by varying the outer radius and the number of patches in the meta surface ring, and arrived at some dimensions that gave us axial ratio less than 3 dB for 1 to 18 gigahertz. Once the antenna and meta surface is optimized, we compared its performance with that of the conventional absorber, means spiral antenna with conventional absorber and spiral antenna with meta surface are compared. What we see here, using conventional absorber, the axial ratio at 1 gigahertz is more than 3 dB. Also, the gain at 1 gigahertz is very low. Instead, when we use our proposed meta surface, the axial ratio between 1 to 2 gigahertz has been improved, and also at 1 gigahertz, the gain is slightly better. So undoubtedly, our meta surface works better than this available absorbing material. So we fabricated the antenna meta surface and fed it through a balloon and covered the balloon with a cap. And here is the thin 5 mm deep cavity, antenna cavity. In measurement, we observed S11 less than minus 10 dB from 1 to 18 gigahertz. We measured the axial ratio to be less than 3 dB throughout the entire frequency range. The right hand and left hand gains we have plotted. We achieved a maximum gain of 8.7 dBIC, and the left hand gain is significantly below the right hand gain. The radiation patterns for two principal planes for different frequencies are also plotted, where we can see the right hand RSCP response preserved over a wide frequency band, wide angular width. So in summary, we have investigated compact spiral antennas by varying different kind of absorbers. So first technique was using a hybrid technique that was effective between 2 to 18 gigahertz, and we saw it was ineffective below 2 gigahertz. So we replaced the absorbing material with a proposed wideband absorbing meta surface, and that structure actually worked from 1 to 18 gigahertz with a high gain and good circular polarization response. Now we go to the next part, where we have investigated beam tilt of compact spiral antennas with a dielectric lens. The challenge, the issue addressed is simply to tilt the antenna beam at one direction, but the challenge is to maintain the tilt angle over frequency. So what we thought, why not to cover half of the antenna aperture with some kind of dielectric, having both real and imaginary part, and see how much does it tilt. So with that idea, we have made a semicircular lens of height h1, and which is placed symmetrically about the x-axis. So we were interested to see how much the main beam tilts from z-axis toward the x-axis, as you can see, from z-axis toward the x-axis. And that tilt angle we have marked as theta t. We have considered a relatively small frequency range from 3.5 to 6 gigahertz. By increasing this antenna height, we could see that theta t actually increases. Okay, so thicker the lens, more tilt we have. But this doesn't convey much information about the tilt. So what we did, we defined 2-3 quantifying parameters. First one is theta average, which is just frequency-wise average of theta t. Theta SD is the standard deviation of theta t, and GM is the maximum gain. So obviously, what we want to maximize theta average, means higher tilt angle, minimize theta SD, that means smaller standard deviation, means at flatter response, with a better GM, means better gain. So with our antenna, with this lens, when we increase H1, theta average increased, but at the same time, theta SD also increased. At the same time, GM is decreasing. So essentially, the tilt angle is increasing at the cost of a inconsistent tilt angle and a low gain. So we try to separate the effect of real and imaginary part of permittivity. So in this part of the table, what we did, we set the imaginary part equal to 0 and increase the real part. What we saw is a significantly high theta average, at the same time significantly degraded theta SD, but with a good gain. In the right hand part of this table, we make the real part equals to 1 and vary the imaginary part. In this case, we got decent theta average, but a low theta SD, at the same time very low GM. So in summary, real part of permittivity can give us a higher tilt angle and a better antenna gain, whereas the imaginary part of the permittivity can give us a consistent tilt angle over the frequency. So with this idea, we just change the geometry slightly, and instead of a flat one, we take an inclined one, inclined or tapered geometry. With the tapered geometry also, we had a similar observation. Means if we increase the thickness, theta average will increase, theta SD will degrade. At the same time, GM will also degrade. But we saw that the tapered lens marginally perform better than a flat lens. So after this investigation, we thought of proposing a new kind of lens where the height of the lens will be varied independently at different radial locations. So the entire 180-degree lens is first divided into 9 sectors. The sector in the middle has the highest thickness profile, and if we go to the right and left, the thickness profile are gradually decreasing. Now if you see, we have considered 4 radial locations, R1, R2, R3 and R4. And at 4 radial locations for different heights are considered. If you now you see H1 and H2 are close to the outer region of the spiral. That means H1 and H2 will affect the lower operating frequency of the spiral. On the other hand, H3 and H4 are somewhere here, so it will affect the higher frequency performance of the spiral. So what we did, we one by one varied all these parameters. And expectedly saw that H1 doesn't have much effect, but H2 affects the tilt angle at the lower part. H3 dominantly affects the middle part of the considered range, and H3 affects the higher part of the frequency range. That means it is possible to selectively tune the tilt angle at different frequency ranges by changing these heights. So after this study, we just optimized the structure and fabricated it. It was tested inside an anechoic chamber. We saw that the S11 is less than minus 10 dB throughout the band. It has good impedance matching. We achieved a maximum RSCP gain of 3.17 dB, and the left-hand gain is significantly or at least 10 dB below the right-hand gain. So we are still getting a RSCP and LSCP gain. We have plotted the theta t response over the frequency range where there is some agreement between the simulation and the measurement. In measurement, we observed approximately 16.8 degree of average tilt with a maximum gain of 3 dB, as I already said. The radiation patterns on the principal planes for different frequencies has been plotted, where we can see that the pattern is tilted at the desired direction with this much amount, almost by theta average. Now the problem we encountered is the material we used is fixed. We cannot tailor the material property. So and moreover, as it is placed above the antenna, the planar compactness of the antenna is lost. So what we thought of designing a meta surface. As you can see here, we had a previous configuration like this, where a substrate was placed above the antenna. Similarly, the substrate can be placed below the antenna, but even if we put it below the antenna, we cannot tailor the property. So what we did, we thought of replacing the material with a meta surface. And despite targeting only the permittivity, real and imaginary part of permittivity, we thought of tailoring the refractive index. What we saw here is the real part of the refractive index. By increasing the real part of the refractive index, the tilt angle is increased. At the same time, if we increase the imaginary part of the refractive index, the responses become relatively flatter. With this idea, we propose this metasurface structure. So in these metasurface structures, metallic patches are arranged over an angular sector of length phi L. This sector has an inner radius R in, outer radius R out. There are different number of patches in the radial as well as in the angular direction, and lump resistors have been connected in between the patches. Now, before optimizing the metasurface, we characterize the unit cell by placing it below a similar three-wire differential line, where we achieved some effective medium properties, which is not equal to 1 or is more than that. So once it is characterized, we thought of parameter or varying the metasurface properties, the geometric properties. Which properties? The angular length, inner radius, outer radius, number of patches in the radial direction, number of patches in the axial direction, and the resistor value. For all these optimization, all this investigation, we had a single goal: to maximize the theta average and to minimize the theta SD. That means maximize the tilt angle, minimize the fluctuation in tilt angle. So with that idea, we selected appropriate values from all this investigation and fabricated the structure, as you can see here. This structure also has been experimentally validated inside a chamber. We achieved an S11 less than -10 dB for 3 to 6 gigahertz. We got a maximum gain of 6.1 dB at 4.6 gigahertz. Also, we had an axial ratio of less than 3 dB for most points in the considered frequency range. Here are the tilted radiation patterns on the desired direction, as you can see. And we also plotted the main beam direction with 1 dB and 10 dB beam widths. In this plot, we saw we have a maximum tilt angle of approximately 28 degree, an average tilt angle of 22.5 degree. So in summary, we can say that this technique actually gives us a more planar profile than the previous technique. It actually gives us a more gain. We are now getting 6 dB gain. Previously, it was 3 dB gain. And now we are actually getting a better average and a better maximum tilt angle. So in summary, we have investigated the design of beam tilt of compact spiral antennas using two different techniques. One, using a semicircular lens made of absorbing dielectric material. The lens geometry we have varied, and we fabricated the device where we got an average tilt of 16 degree with good gain. In the second work, we have replaced the lens with a metasurface, where we varied the metasurface dimension to get a better tilt, a better gain, and a good circular polarization response. Now we come in the last part of our work, which is reconfigurable metasurface with patch antenna using channel modulation. So the theoretical technique, this is obviously the second part. So it is associated with the wireless application of our thesis of metasurface. So we used a technique called media-based modulation. What is there is it has a transmitting antenna and it has a reconfigurable screen placed in front of the antenna. The reconfigurable screen is actually reconfigured using the transmitting symbols. An oscillator continuously drives a power, a single tone through the antenna. Depending upon the switching state of the metasurface, different magnitudes and phases are transmitted. And these different magnitudes and phases are actually decoded as data in the receiver. So here is the unit cell of the reconfigurable metasurface. You can see there is a meander and two horizontal strips, and a pin diode is placed in between the strip and the meander. The entire metasurface is only 10 mm by 10 mm, so it is lambda by 7.5 at our operating frequency of 4 gigahertz. What we can see here, I have plotted the S21 for two configurations, diode off and diode on. When we turn off the diode, the S21 at 4 gigahertz is -1.5 dB. Whereas when you turn on the diode, the S21 falls to minus 20 dB. So essentially by turning the diode on and off, we can control the transmission of power through the unit cell. Next, we have designed a simple rectangular patch antenna which simply radiates at 4 GHz. Once the unit cell is designed, the next objective was to determine what should be the size of unit cell and what should be an optimum distance between the antenna and unit cell. To determine the size and unit cell, what we did, we placed a different size unit cell in front of the antenna. That means from 4x4 to 10x10. Then we considered two states. One is transmitting state, one is blocking state. In transmitting states, all the metasurfaces are turned on. In the blocking state, all the metasurfaces are turned off. So maximum power will be transmitted in the transmitting state and the minimum power will be transmitted in the blocking state. So what we did, for different array sizes, we first determined what is the maximum power transmitted. Means for which array size we are getting the maximum power when all unit cells are on. We find that when the array size is 8x8, maximum far field power is achieved. Similarly, we defined another parameter called delta magnitude, which is the difference between the maximum and minimum power. What we saw, if we keep increasing the array size, this difference may increase. But since we are getting the maximum power at 8x8 and making the array size bigger will complicate the overall system, we thought of considering 8x8 for our design. The next is to optimize the gap between the antenna and array. For that, what we did is we placed the 8x8 array in front of the antenna and varied the distance and saw for which distance we have matching for maximum number of switching states. What we found that for when the distance between the antenna and metasurface array is approximately 40 mm, we have matching for we have maximum number of switching states and S11, which is less than minus 10 dB, minus 15 dB, and minus 20 dB. Also, this 40 mm is approximately close to lambda by 2. And this was actually theoretically shown by another group of work that there will be the least mutual coupling between these two devices when they are lambda by 2 apart. So our structure is finalized and this is how it looks like. It has 8 rows and 8 columns and we used a single input to control all elements of the column. So essentially we have 8 columns. Therefore, we need 8 input lines. 8 input lines means we can have 2 to the power 8 combinations. Means 256 switching states we can have. Okay. So for all 256 switching combinations, we have plotted the magnitude and phase of the radiation pattern. You can see a significant difference in the magnitude and phase for these 256 cases. Now this magnitude and phase has been translated into complex data called constellation diagrams at different angles for theta equals to 0 to theta equals 60 degree. The interesting point is at different angles, the constellations are different, and we'll see the advantage of this in the later slides. Now comes the fabricated prototype. Here is the metasurface. Here is the metasurface with the antenna. It is the current driving board which actually drives this diodes in this board. How things work is a Python interface in a laptop that generates the data to be transmitted, and accordingly the metasurface is set. Once the metasurface is set, the Python interface asks the VNA to record the complex S21, and that's how it continues to work. Now we have performed the experiment in different environment. First is in scatter-free and scatter-rich environment. This is to understand what is the effect of scattering on the overall performance. For that, what we did inside the anechoic chamber, we placed the metasurface at a constant point and varied the receiver. In the receiver, we have used a simple horn antenna. Varied and placed the receiver at 4 different distances. These distances are almost lambda by 4 away from each other. We have plotted the constellation diagram for these 4 distances. What we can see, for different distances, we have different cluster of symbols, and the change in lambda by 4 has resulted in 90-degree phase shift in among the constellation. That means the phase change due to the distance change is perfectly reflected in a scatter-free region. The same experiment outside the anechoic chamber, means in the laboratory environment, you can see there is no phase change observed. Means the phase information with the changing distance is lost in a scatter-rich environment. But since we have to work, we have to deal with a real-time environment, we have to go for a scatter-rich environment. So in the next investigation, we have carried out experiments in scatter-rich environment in line of sight and non-line of sight configurations. Two line of sight and two non-line of sight configurations are considered, and you can understand this is the schematic of measurement area arrangement inside our microwave laboratory. These photographs are also attached. Now, in all four cases, we have collected all the constellations, and from each of them we have selected four best symbols. This symbol selection has been done based on some Euclidean distance-based measure. Now, the first observation is in each case we have unique constellations. Means the data set for each configuration are different. Second thing, we have plotted the bit error rate response, where the line LOS1 and LOS2 have overlap, whereas NLOS1 and NLOS2 are non-overlap, and they are better than LOS1 and LOS2. So the first conclusion that comes from here is in line of sight scenario, since the direct power dominates over the multipath power, we do not see any change in the bit error rate response. Whereas in a non-line of sight scenario, we do not have any direct power. Hence, the entire communication is dominated by multipath power. Now, the interesting thing, when we are communicating using only the multipath power, we are having a better BR response. So we are doing nothing in our hardware. We are just working in a scattering environment, in a non-line of sight multipath environment instead of a direct environment. And the environment itself is helping us to improve the bit error rate response. And this actually was the prediction by the MBM theoreticians. Now, in one of the last investigation, what we did, we tried to analyze a multi-user scenario in a non-line of sight configuration. So the transmitter we set at a single location, and three different users has been placed very close to each other. These three configurations are marked as NLOS 3, 4, and 5. And by the color, you can understand these are the constellation for NLOS 3, NLOS 4, and NLOS 5. So the first observation is NLOS 3, 4, 5 have different set of constellation. Means if the user location is changed, immediately the constellation is changed. Now let's look deeper into these diagrams. First, we have selected four symbols from NLOS 3. You can see that is marked as C33. These four switching states or these four symbols has been printed or has been plotted for NLOS 4 and NLOS 5. Now you see these base four selected symbols are well away from each other, whereas when we plot the same symbols in other two constellations, they are not the best symbols for them. Okay, that means the best symbol for NLOS 3 are not the best symbols for NLOS 4 and 5. Similarly, the best symbols for NLOS 4 are not the best symbols for NLOS 3 and 5. So we can say that different users sitting at different location are communicating with a single transmitter using different set of symbols, which are mostly non-overlap, mostly. So this actually, shows a energy and power efficient transmission for a D by D constellation, and this is typically termed as D times energy harvesting. Another thing, when we change the user location, the corresponding multipath changes. So no user will know about the constellation of his neighbor, because at the neighbor, the set of multipath is different. So this inherently makes the entire communication secure always all the user will remain oblivious about the constellation of its neighbor. Then at the last investigation, what we did, we have collected 15,000 symbols and drawn the statistical distribution of both real and imaginary components. One interesting thing that we saw, that we are communicating in a scatter-rich environment, which is a Rayleigh environment. But when we draw the constellation and make their distribution, they came out to be Gaussian. So right now it will be, it will not be a good time to make any conclusion out of this observation, but which is a part of future work. But we can say that if we communicate using the multipath components of a channel, it may be possible to achieve a capacity of a Gaussian channel despite being working in a non-Gaussian channel. But these are all a part of a future work, and it needs currently beyond the discussion of this presentation. So using the same hardware, we have carried out some data transmission, and whatever we transmitted, we actually received back correctly. So here are the conclusions. So we started investigating compact spiral antennas using metasurface. We made a reference antenna that works for 2 to 18 gigahertz. We placed the antenna at different heights above a flat ground plane. And then consequently, we proposed a conical and truncated conical geometry where we achieved good antenna again with circular polarization response. In the next step, we have removed the truncated conical geometry. Instead, we placed a flat metallic geometry and placed the antenna extremely close to that. And in that case, the low frequency degradation have been addressed using absorbers. So the first absorbing technique we used is a hybrid absorbing technique using lump resistors and absorbers. That gave us a good axial ratio for 2 to 18 gigahertz, although it could not work below 2 gigahertz. So for below 2 gigahertz range, we replaced the absorbing material and placed a wideband metasurface, and we got an extremely compact antenna that worked well with good gain, good axial ratio, and good impedance matching. In the second part of this work, we investigated the beam tilt using two different techniques. In the first technique, we have made a lens of a absorbing dielectric material. The lens profile is varied, and what we got is approximately 70 degrees of tilt and 3 dB of gain. To improve the compactness of the structure, we removed this lens, replaced the lens with a metasurface, and we got a better tilt angle as well as a better overall gain and circular polarization response compared to the previous technique. In the last part, a digitally reconfigurable metasurface we have investigated for media-based modulation. We experimentally demonstrated that the multipath component inherently present around us can improve the performance of the system, and a better multi-user system can be built by exploiting the multipath components in the channel. Here comes the future work. All the miniaturization here I have talked about is regarding the distance. So the miniaturization is always in the vertical direction. No horizontal miniaturization has been discussed here. First thing. Second thing, all the impedance matching and axial ratio improvement are discussed in the lowest frequency or low frequency region, where I have simply ignored the low gain at the low frequency. So this can be a part of a discussion where the gain at the low frequency should be addressed. A frequency time-based analysis of a spiral may be done, which is sort of an open-ended suggestion, but I feel that can be beneficial to understand the working of the spiral in a better way. Another thing, we place the balun, we consider the balun as an additional thing. I mean, if the balun was kept outside the antenna cavity, so if we can fabricate the balun or integrate the balun inside the cavity, that spiral design can be directly usable for any commercial purposes. For the beam tilt operation, honestly, we are the first group who actually have some results regarding the beam tilt of spiral antenna over 2.5 to 3 gigahertz band, which is not there anywhere in the literature. But this 2.5 or 3 gigahertz is much, much smaller compared to a 2 to 18 or 1 to 18 gigahertz spiral antenna. So we need more investigation to see how we can increase this bandwidth. Another thing, we need a better understanding of this tilt angle, that how well we can steer this tilt or can increase or decrease the tilt, which is still missing in our current work. For the last work in MBM, we have to measure the channel capacity, which has been also suggested by the reviewers and also felt very much important by us, by our current group. So this channel capacity measurement of mutual information is very important for this. Another very big disadvantage of our current system is it is very much sensitive on any change in the scattering environment. If there is a minute change, that will be reflected in the performance of the system. So this system we have to address either by doing a faster channel estimation technique or by using some prediction or prediction related thing, so that we can predict how the channel will change if one chair or one table moves around the scenario. So these all may be considered in the future work. So these are the publications that came out over the years from all this work. So I would like to I would like to acknowledge these people. First is obviously Professor Binoy for giving me the platform working in ECE IISc, and for selecting me for this IISc Ubio Thales CNRS collaboration project. And also I would like to thank you for his guidance, his technical inputs, and patience, and his encouragement for excellence. I would also like to thank Professor Cedric for his technical input, guidance, for considering me for this collaboration project, and also for hosting me in Labstick and giving me all facilities for research that I required. I'd like to thank Professor A. Chokalingam for his technical input and guidance, especially for MBM related work. I thank Dr. Noham Martin for his guidance and support, and especially for being the best friend in France. Dr. Stephen Malagol, who actually technically helped me a lot in the domain of spiral, and even for understanding the spiral and how to do the measurement of the antennas. Mr. Christian Renard for his technical contribution for improving the manuscript. And obviously the co-authors, all the co-authors of my work who significantly contributed to continue my work, to write the manuscripts, to revise them, and without their effort, it was not possible to complete my work. I would like to thank Microwave Lab and Labstick for giving me the fabrication and experimental facility. I would like to thank CNRS for conducting this joint collaboration between the institution, industry, and that helped me to explore much more things beyond PhD. I like to thank Government of India and Thales DMS for funding. ECE, the former and the current chairman of ECE office in UBO, CMI Brest, for assisting me to complete all necessary official activities. At the end, I would like to thank all of my teachers who actually assisted me, who guided me, who pioneered me to see this day to day. I thank my parents, my wife, my family members who were there and who pursued me to carry such a long academic career, and still there at the age of 30, I'm a student. So still there with me. I would like to thank them from my heart. At the end, all my colleagues, juniors, seniors, I cannot put in a list of them or name of them because it will take slides if I put names. But without them, it would be a blind journey for me. You make all my journey special. Thank you everyone for being here. And at the end, I would like to thank late Ritesh, who was my senior in PhD, who helped me and guided me to grow and mature in all dimension most of the dimension in my life. So that's all with these remarks. I conclude. If you have any questions, can let me know. Thank you.
Media-based modulation work that you were doing. So essentially,
Yeah, one work is completely on downplane.
is how exactly that helped you in if you are changing the ground plane, the small portion you have changed, or you have changed the complete ground plane, like we have started with some stake-like structure and can explain that.
Yeah, so the reason is more historical than technical. So actually, we the way I have explained it is the same way we explored. So we just saw that what are the effects at different heights. So despite going to the step structure, because I already talked to a few people who said that they have worked on step structure and they did not get success. Then in one paper, I found such kind of a conical geometry. So when I simulated a conical geometry, then I could see that there is a relation that if it is conical then flat, then actually it is adding up all the benefits of flat at different heights. So then sort of in that stepped in the two-step work, there they have performed some radial calibration or radial change of the structure. So I just thought of putting both of these ideas, and that's how things came. I mean,
Portion of the ground plane is the complete ground plane means what I'm saying. So we were a 3D kind of structure we are using. And ground plane could be some dimension. Suppose x cross y dimension is there. The complete dimension you are not modulating.
Yeah. If I show you the this one, so this is how it actually looks like. So this white thing you can see, this is the white thing, and this is the top side of the white thing, and
this the bottom part is showing some.
This one?
Is that the shape or that one?
This is the shape. This is the shape, and this is the bottom side, so it's flat. On top of it, there is this truncated conical. This is the flat section, and this is the conical section, or the.
It is helping improving the axial ratio part.
It is helping the axial ratio. It is helping the gain flatness. That was our, stronger claim that we are making things flatter. Obviously, axial ratio will be better because at low frequency, problem is at low frequency. So at low frequency, we have a higher, more height, so axial ratio will be better. But we said that we are making these things flatter. The gain is we are making flatter. That's all.
Next is that in slide number 26, we have used one deep and kind of structure, but okay, go back one is
this one.
One deep kind of structure you have made over the antenna. Yeah, this one. So how exactly the height you have decided?
Okay. So this reason was slightly intuitive. When I simulated this structure, I saw this kind of response that a tilt is there, but tilt is changing significantly. Whereas when I did this kind of structure, I saw that things are much more smoother. So I thought that there should be tapering in both the directions, both in angular direction as well as in the radial direction. That was the first thought. In the next thought was that, see, in this structure also there is a angular tapering. It's from center to this side and that side. Tapering is there. But the idea was that why should I put a straight thing? I mean, first I put one single point. I made a single point and varied the height, then made 2 points, and then I came with three intermediate points. And that, since that was sufficient, I did not increase it further. But it can be made smoother if we take more points. But
some parameterization
not exactly the parameterization is obviously the final tool. But before that, the intuition from this structure that there should be tapering so that the fields from the spiral should gradually encounter with the lens and then again gradually be relaunched on the spiral. So this intuition actually, exactly, that's what I used for designing this structure. Sorry?
One side of the antenna you use this part.
Yes.
Other half is still
it is empty. It left no covering.
How exactly this
So
because in general people try to increase the gain or something. In general, the gain lensing structure you are trying to incorporate. Overall antenna they used to cover to get a converged beam and all. So you have used the side. So what is the reason for you?
Yeah. That reason lies in the basic working principle of the spiral antenna. That why covering half of the aperture is not splitting, instead it is guiding entire thing. It is because if we see this diagram, half of the result is half of the answer is here. So it makes a current ring for radiation, and on the current ring you have from it is since it is lambda long, its length is lambda. So we have all the angles, all the phases 0, 90, 180, 270. So the lines coming up from left side will terminate on the right side. It's not like a patch antenna that lines from patch is being terminated at the ground. It's not like that. The lines are starting from the spiral and are ending on the spiral. So I thought, why not to weaken the field in one side? So the force in one side is more and one side is less. So
for this or broadside radiation?
This is broadside radiation. When I load half of the antenna, then obviously one side is weakened or changed. Phase and magnitude is changed because
I think you are trying to tail the particular direction. That's
yes.
Why the
yes.
It's very interesting. Means how exactly you have configured that particular structure.
Oh, okay. Maybe yeah. We used a 3D printing machine to print this profile. Okay. This is, see, ABS is a wide class of material. ABS is not a single material. So some typical ABS was used, but some things were slightly classified here. So even it was not, yeah, it was the available thing, but it has a carbon loading. That is why not only is black, that is why it has a lossy part. Okay. So ABS is a wide class of material. It is not the exact material, but this is what was available.
It is not disclosed.
Dielectric property is partially disclosed. Dielectric property is partially disclosed only on the frequency of interest. Okay, so this was the property we used, but the material name and etc. was not completely.
So it's a part of the.
Yeah, it was a part of that
industry collaboration.
Sort of.
So which application is?
Okay, so since the time is less, so I could not elaborate everything. It is sort of if you place it with a ship or in an aircraft. Okay, if an antenna is directly look below towards the ground, it may not be useful because the enemy may be there. So you can say that you tilt the antenna, but not always we have the luxury of tilting the antenna in a complex structure. So it was sort of an investigation to see if it is possible to keep the antenna like this and tilt an antenna beam at a certain direction. That's what was a typical application.
Last week you have mentioned on parameters for the standard deviation of angle.
Yes.
What exactly the artery of the clustering for?
So this standard deviation you are asking. So see, standard deviation means a deviation from the average. So what I want a flat curve here. I want a flat curve means less standard deviation. Okay, since there are variation with frequency, so I wanted to define a parameter that shows the variation of
The
frequency.
flat response you want that you are defining in standard deviation. That's what.
I mean, if the standard deviation is small, then it is flatter. That's what I wanted to see. Okay, that is why you see everywhere the standard deviation. I'll always say that if the standard, I am trying to minimize the standard deviation and maximize the angle.
Deviation from which particular values?
Theta average.
Theta average. Okay, thank you. The nice presentation, nice story.
Thank you.
Congratulations.
Thank you.
There are questions in the comment.
Okay, so Polomi has posted one question. What challenges did you face in designing the balun? Because it is a wideband application also before placing the absorber near ground plane for improving the gain. Did you try designing planar structure in ground plane for improving, before placing the absorber near the ground plane for improving the gain? Planar structure in ground for improving the gain. First part is clear to me. What are the challenges I faced designing the balun? See, thank you for asking this question. The challenge, there was not much challenge. It is because the balun we used is already there. Okay, so we just had to find out two parameters. What should be the strip width to match the impedance, and how should we change the geometry of the strip so that the balancing and unbalancing is countered. So there was not much challenge. It is already available in the available literature. For the second question, before placing the absorber near ground plane for improving the gain, did you try designing planar structure in ground plane for improving the gain? I assume that she is asking if without an absorber we can address the gain. I'm not sure, but okay.
Yes, I'm asking the same.
Okay, so that is the question is, okay. Yeah, so similar thought, a very similar thought we had, but we faced with challenges. What I thought, why not to directly kill the wave? Why not to pass it through some other path so that the same effect can be there with a better antenna gain? But unfortunately, I was unable to do so. But it can be a future work, and as I also mentioned in the future work that at low frequency the gain is issue, but I was unable to do it without an absorber. So I think I answered your question, and
Yes, thank you very much.
okay. Anyone else? Yes, please.
So in the media-based modulation, you said different users are receiving different constellations, right? So for example, in typical communication, what happens if you, let's say the base station is transmitting, for example, QPSK, then there are only 4 constellation points. So the users know out of these 4 points only, something has been transmitted, right? So in your case, let's say you had that 8x8 array. So you said there are 256 constellation points, right? Now, if a particular column has been turned on and all other columns are turned off, right?
Okay.
So wherever the user is in the room, they should be able to decode, okay, that is the particular column that has been turned on and other columns are turned off. So if despite this case, you are saying they are receiving different constellations, while at the same time you are just turning on one of the column, that is not making sense, right?
No, it depends that users sitting at different places will obviously receive different magnitudes and phase for a single whatever you said turning on one column.
Correct.
So in the channel estimation technique or that pilot transmission itself, different users has to know what is the magnitude phase for that particular switching combination. Once it knows that, only then it will be able to decode.
Yeah, no, but how do you say that they are receiving different constellations? That constellation, is it you are just talking about that magnitude and phase variation that is happening because they are seeing different channels, each user seeing different
Yeah,
channels?
that's all. I mean,
That
there's
happens everywhere, right? I mean, let's say if base station is transmitting from a QPSK, if you sit there, I sit there, then if you are seeing that the channel they are seeing different magnitudes and phase, then it's not right to say they are receiving different constellations. Right?
no, it is not exactly like, I mean, it's kind of a overlap between these thoughts.
Yeah.
One is for QPSK thing that we are saying that it is sort of a broadcasting, because they know that once I decode it, I will get this. But here, even in a single sitting, single environment, it is possible to communicate to different user, maybe in a TDM mode or whatever be, to transmit different informations. Okay, by exploiting these different multipaths. So it is not like a typical broadcasting in QPSK, that kind of thing. So
Okay.
is it okay? I mean,
Yeah, I was just confused between that each, despite having only one combination, one column turned on, each user is receiving different constellations. So
okay, so one thing is, since the constellation is a direct interpretation of magnitude and phase, that is
phase of the entire channel or only the
for
screen that you are
for a particular user transmit receive pair.
for a particular user transmit receive.
Okay, I maybe show you. Sorry.
Yeah, well, okay, I can just simplify my doubt. One doubt was the magnitude and phase that is coming because of the particular column that you have turned on the screen.
Correct.
And there is one magnitude and phase that will come because of the channel itself. That is the after the what we can say the wave emits from that screen, then there is because of the chair and all. So that magnitude and phase variation will be obviously different for each and every user in typical communication constellation as well, and is in your case as well.
Yes.
Yeah. So that's what the question.
See here also, if you see, it is theta. So at different theta, the constellations are different because the antenna is radiating in over a certain angular direction, and at different angular direction, the magnitudes and phase are different itself. So before passing through, I mean, after passing through the screen, it is reflected. That is one issue. But before that itself, we are sending different magnitudes and phase and different theta values. That is itself is there. After that, again, it is getting reflected at the intermediate medium and the receiver. Yeah, sure. See, this is the magnitude and phase plot for theta, different theta values. Okay, theta is this plane, ZX.
Yeah,
okay, theta is minus 90 to plus 90. Now we have transferred this magnitude and phase into complex data for 5 different theta, 0, 15, 30, 45, and 60. We have shown the constellation. Okay, now since for different theta, the magnitude and phase are different, obviously the constellations will be unique.
This data is with respect to exactly where are you measuring this data exactly? I'm a little bit confused.
Okay, no problem. This theta is on the ZX plane from minus x towards plus x.
So this magnitude theta, where are you measuring at the receiver end or at the transmitter?
This data we have generated using CST, and these are the far field magnitudes and phases. Okay, if you simulate one antenna, you will get one magnitude and one phase in the far field. So we have done the same for 256 combinations. Okay, then for different theta angles, for us like 0, 15, 30, 0 is here, 15 here, 30 here. For these different angles, we have determined the constellation. Since the magnitude at 0 is different from magnitude at 15, magnitude at 30, similarly for phase, obviously the constellations will be different. Complex data will be different.
Correct. Okay. Yeah.
Is it sort of?
Yeah. And one more thing, like, is it like if you know there are multiple antennas at the transmitter end, then there is some way like you can do some beamforming, like beam steering or something, right? So is there any way like are you is there any way in NBM we can do the same thing by using just the single antenna by using the screening?
Truly speaking, that is what people do. And this is something that people don't do, we're trying to do. So we are trying to avoid the technique and terminologies of beam forming and steering, because that's what people conventionally do. So here we are just saying that we don't need any forming steering. Whatever we have, we can communicate using that.
Thank you.
Anyone if you? Sir?
No other questions, then, thank you. Thanks, everyone.
Okay.
We can move separately.
Okay. Okay. Sir. Who is? Purango, you? Okay.